from again Tarleton State University, and he's going to continue to talk about n-body problem and adaptive optimization of lattice towers.
Hi, I'm Jaryd from Tarleton State University, and this is the n-body adaptive optimization of a lattice tower. So, a lattice tower is a freestanding structure made of a framework of beams connected at nodes. So the Eiffel Tower or radio towers, most common to us are power transmission towers. Now there are about 27 million transmission towers in the United States, costing tens to hundreds of thousands of dollars each. And that's mostly in material costs. So we'd like to use less material, make the tower lighter and cheaper, but a tower that falls over costs twice as much. So we would like to make sure that it stays strong, it's still sturdy, without wasting materials in the process. And this is the key dilemma in our optimization problem. Thicker beams are stronger, but they're also heavier and more expensive. Thinner beams are lighter and cheaper. So you can view this problem as a dispute between a construction worker and a businessman. The businessman wants cheaper beams, and the construction worker just doesn't want the thing falling over. So they reach an agreement by setting various constraints, like a allowable strain, or amount to which the beams can compress or stretch. And what we're doing here is called truss sizing optimization. We're taking a tower and resizing each of its beams to make it as light and cheap as possible without sacrificing structural integrity. Now, the method we've come up with for doing this is based on our muscles. So if you work out your muscles, they grow. You don't use them for a while, they atrophy. So a member that's under a lot of stress will get stronger, will get thicker, to better support the load it's under. And a member that's not under so much stress will atrophy, becoming lighter and cheaper. And it's important to remember here that the variable we have in this optimization problem is the cross-section of each member or group of members. Now, truss sizing optimization is a money problem, so a lot of people are working on it and a lot of algorithms have already been made for it. Most of these are population-based search algorithms. Now, what are they searching exactly? Let's start with this example tower. It has 5 members and 4 nodes, and the members are divided into 3 groups, X, Y, and Z, based on symmetry. So there are effectively 3 variables describing this tower: the cross-sectional area of the groups X, Y, and Z, each constrained within some allowable range. So if we put these variables on axes and constrain them to their allowable ranges, we get a box. This is the set of all the towers we can make. For example, in this bottom corner is the tower whose members are all as narrow as possible. If we move along the AX axis, we get a tower with thicker X members, and up in the top corner is the tower whose members are all as thick as possible. And this is the search space. Its dimension is equal to the number of groups we have. So if you have 16 groups in your tower, there are 16 dimensions in your search space. Our largest tower has 59 groups. So as you may imagine, each of these towers has some quantifiable goodness or fitness based on its weight and whether or not it meets constraints. And the goal of any search algorithm is to find the most fit tower in some limited computation time. Now, population-based search algorithm starts with an initial population of towers or samples, and through some set of rules, iteratively moves around the search space looking at new towers, new sizings, until at the end of its computation time, it reports back with the best one it's found. Now, these rules may be based on gravity, as in the gravitational search algorithm, or may be based on the breeding and mutation of solutions, as in the simplex crossover method. More advanced and recent algorithms use a mixture of these and are quite complicated. So the other algorithms we've been comparing to follow 2 basic principles: exploration and exploitation. So you can think of exploration as taking wide steps around your search space, looking for regions that have good towers in them, and then you exploit those regions, finding the best one in that area. Ours proceeds differently in kind of a smoother fashion, less step-based. We start with a sample of towers and then refine each of them slowly until they get to the best that they can be. So this kind of looks like naive gradient descent, if you've heard of that, which basically means look in my immediate vicinity. Okay, that one's the lightest. I'm going to go there. Look for the lightest one, go there, which tends to get caught and doesn't find very good solutions. But our searchers aren't trying to minimize weight. They're trying to redistribute strain in such a way that you're not wasting any of the material you have in your tower. So it's slightly different, but it works better than gradient descent. And it produces some interesting patterns. But before we get into that, I will have to describe to you what colors we're using here. So red is going to represent compression. Blue will represent tension, with green being a neutral color. And then any member that's close to its target strain will be in yellow. And the thickness of the member on the screen is proportional to its cross-sectional area. So what you see here is a section of a torus before adaptation. The members in green aren't supporting much weight and will tend to atrophy, while this red spine in the back is load-bearing and will tend to get stronger. So this is occurring in real time. Very quickly finds a nice distribution of weight and sticks to it. So that red spine in the back ended up being a nice thick beam. This is, our algorithm is very good at finding lines of action within the structure and reinforcing. So there are 9 different standard towers that we were comparing to with other algorithms. The simplest, and also one of the only ones with 2 loading configurations, is the 72-bar truss. So the first loading configuration is simple. It's a force directly downward at each of the top 4 nodes. And this produces kind of an obvious result, which is that if you just have perfectly downward forces, all you really need is columns supporting them. And this result differs from other algorithms in that other algorithms do not see the vestigialization or the complete narrowing of these cross members on the side. They still have some weight left. And the result of that is that this result is 1/3 of their weight. The second loading configuration is a diagonal force on that back top node. And again, you see the kind of disappearance of certain members as the algorithm decides they're not necessary anymore. And this time it produces a less obvious pattern, but still beautifully symmetrical. Right, so this next tower is not one of our standard towers, but it does show off our algorithm's ability to deal with dynamic loads, so loads that change over time, which other algorithms cannot model. So in this case, the tower is in an earthquake. It also has cable weights, so like power line weights, hanging out of each of those points up there. And the adaptation stabilizes it over time. So the things we can model are really limited, or the things we can adapt are really limited by what we can model, which is basically limitless. This is an icosphere like the Reunion Tower in Dallas. And this is just a torus, very effective at the torus conference. And so everything you've seen just now has been a best of 1 run, done on the CPU. So we've run it once and got a result. But recently we've got this working on a GPU, which means we can run over 1 million of these things at once, over 1 million different adaptations all at the same time, each with their own unique parameters and constants, all converging at the same time. And it only takes a matter of seconds. And that is our future. So, that's all. Are there any questions?
On the sphere simulation, what forces did you use to simulate?
What forces did I use in the sphere? That is just self-weight, so just
Okay.
the weight of the members. Yes?
So you mentioned muscles?
Yeah, it's all based on
Yeah,
muscle.
those that you have a license for those?
No, I don't. I keep them concealed.
Well, so are you able to optimize muscle growth then too? Are you-
Oh, like actual biological systems?
Yeah.
We haven't tried that, actually. But that's a total possibility. Yeah. Any other questions?
Questions?
You good?
Yeah, let's thank our speaker one. And our next talk will be at 10:40. Like, did you one of them was like against the earthquake?
Yeah.
What other greens might be?
Oh, yeah. We can apply wind loads and basically anything you can think of. Anything you can, really just anything. So like icing conditions, like adding weight to it during weather.
So like, I don't know, it depends on how tall is it, the weather condition will be different. The top part will be maybe cooler than the bottom part.
Yeah, so you might get more ice formation on the top of it, which would weigh it efficiently.
Yeah.
But yeah, we could do all that. And that would be.
But you haven't at that one, those type of things yet.
So our biggest deal recently was getting it to work on the GPU, so having a lot of things running at the same time. And after that, we can do whatever.
Look at some,
We can really start working with it. Yeah. All the flavors.
Thank you.
Oh, I don't know if I